Hi, and welcome back to Geology. I'm Miss Sparks, and today I want to walk you through on how to find the half-life of an element. And so I feel like sometimes students are always like, oh my gosh, math in science, but it normally comes hand in hand, and in our science it does as well. Today we're just really going to focus on how we can find the half of something. So we're going to either be multiplying by 0.5 or dividing by 2. So not too terrible that we have to kind of work through a couple of things. So far we have been talking about the idea of absolute and relative age, and radioactive decay has to fall underneath that category of absolute age. Being able to identify how old either a specific rock sample is, or even sometime actually figuring out the actual age of a organism that was once living. And so that has to do with normally two different types of elements, which is our uranium and our carbon. And today we're going to kind of be adding to that just a little bit. What are some different ways that we can look at them? And so you are going to want a calculator today to kind of work through today's activity. And I'm going to show you two different ways in which you can kind of find and solve for how old a sample is. And so yesterday we kind of looked through and talked about the different ways in which our parent element can decay down into our daughter element. We talked about those changes of rates, that natural clock cycle that's going to never ever change with an element, releasing its nuclei out into the environment. And so that's what we're going to look at today. So let's look at this example right here. So the first one says radioactive iodine. So we're talking about iodine this time, which is fine. It is still a radioactive element. 131 has a half-life of 8 days. So this is fast. So imagine every 8 days it releases a nuclei into the environment. So 8 days, bloop, into the environment. Another 8 days, so 16 days, bloop, 2 have now gone into the environment. And so we're going to kind of look at what that means. And so we have, let me just kind of underline a couple of things. So this is really important, the half-life of 8 days. We have an original amount of 400 grams. And we want to know how much of that 400 grams is left after 32 days. And so we're kind of breaking down how many times this half-life is going to go through in this 32 days, and then kind of apply that into a couple of different categories here. So it's kind of like a twofold event that we need to look at to help us solve for this. So the first is, how many times can 8 go into 32, so we can figure out how many half-lives has this sample gone through. So all you're going to do is take 32 and divide it by 8, and that's going to give us 4. So that means that it has broken down 4 times, meaning that we start out with 32 days, we count out 8 days, bloop, a nuclei passes through. Count out another 8 days, bloop, another one. And so it can do that at least 4 times within that 32-day sample. So next we're going to look at our sample of 400 grams and then break that down in half 4 times. Or if you want to multiply it, I gave the example of multiplying it by 0.5. Or you can just take 400 and divide it by 2. Whichever way you would like to do it will be fine. So we're going to start with that 400, and then we're going to divide it by 2. And that gives us that 200 right here. So that's our first half-life. Then we're going to start with the 200 and divide it by 2 again. So 200 divided by 2 gives us 100. That's its second half-life. Now, we have 100 grams left divided by 2. We've got 50. And then finally, our 50-gram cycle, or 50 grams, and we have one more half-life that it has to go through. So we'll take 50 divided by 2, and that gives us our 4th half-life. So we started with 400 grams, and by breaking it down 4 times, we end up with then 25 grams left after that 4 half-lives. So 25 grams is how much would be left after 400 grams after that 4 cycles. Now it's asking find the amount of iodine 131 left after 32 days if it was 144 grams. So we're just starting with a different gram amount. Nothing else has changed. We still got the 32 days. Remember, 1 half-life equals 8 days. And so we know that once again, 8 will go into 32 4 times. So we're going to break this down 4 times, 4 half-lives. I'm going to write it like that. So let's just kind of take a look at what that looks like. I'm actually going to use a text box for this. I feel like that will be a little bit easier for me. So once again, we're starting with 144 grams. And we are going to divide that by 2. Or divide it by half, I guess, if you want to think about it, divide it by 2. So 144 divided by 2, that gives me 72. 72 grams. And so now, that's 1 half-life. Now I'm going to do that again, divide by 2. So 72 divided by 2, and that is going to give me 36 grams. That's 2 half-lives. Then we're going to do 36 grams divided by 2. And that gives me 18 grams. Oops, I forgot my equal sign. So we got 18 grams. I'm going to move this over here so I can have a little bit more room. 18 grams, so 1 half-life, 2 half-life, 3 half-life, 1 more. So 18 grams divided by 2. And when I divide 18 divided by 2, I clearly get 9 grams. And so that's my final sample right there. So starting out with 144 grams, breaking it down into its 4 half-lives gives me 9 grams left. So I didn't change it too much. The next couple ones, you just have to work out the problems. This one says if you have 1,000 grams of iodine, 131, half-life is still 8 days, how much time will be left after 32 days? Haven't changed a whole much. You're just going to start with 1,000 grams. So you're going to start with 1,000 grams and then move it down, breaking it in half 4 times from 1,000. And then the same with 300 grams. So once again, just changing the gram amount. Let's look at it vice versa, the other way around, meaning that let's say that I give you the actual ages of things and then we have to go back and figure out, well, I give you the grams and you have to figure out the age. So this example here says a certain radioactive element has a half-life of 8,500 years. So every 8,500 years, a nuclei is released into its atmosphere. The parent element is broken down into a portion of the daughter element. The original sample contains 8 grams of the radioactive element. The current sample now only has 2 grams. So it started at 8 and has degraded down to 2 grams. Parent element started at 8, now it's at 2. How old is this sample? So a couple of different things is first we want to figure out how many half-lives has this broken down into. So we have 8, so we're going to break it down. So take half of the original sample and continue multiplying it by 5 or dividing by 2, whichever way you want, until you get to the point where it's degraded down to the 2 grams. So for example, we have started with 8 grams. If I divide that by 2, I've got 4 grams. If I take 4 grams and divide that by 2, that should be equal. I end up with 2 grams. So there's 2 half-lives in the sample, meaning that it started at 8, broke down once, and then broke down again to get to 2. So we know that 1 half-life equals 8,500. So we're just going to add 2 half-lives together. So 8,500 plus 8,500 gives me 17,000 years. So this sample, how old is the sample? The sample is 17,000 years old because we could see working it backwards with using the amounts and moving into the second half of it. All right, let's look at another problem here. So this one says, use the sample from above, find the average sample if its original amount is 36 grams and the current amount is 9 grams. So we just have to figure out how many times we can break down 36 to get to 9. So kind of the same idea. I'm going to do a text box. We're going to start with 36 divided by 2, and that equals 18 grams. So then 18 grams, got to make it all the way to 9. Divided by 2 equals, clearly that's going to be 9 grams. So once again, 2 half-lives this time around. So same idea is that we are now just going to, so 2 half-lives. 2 half-lives. And they didn't change anything from above, so we're still going to then add 8,500. And you can multiply it by 2 if you want to. That will work the same. And when you multiply 8,500 with 8 times 2, you still get that 17,000. Whoops. There you go. Years. Perfect. Same idea. This one here. So you've got a few extra ones. So let's look. The original sample was 28 grams and the current sample is 7. How old is the current sample? So same idea. Still have a half-life of 8,500 years. So we're going to start with 28 grams. And we're going to divide it by 2. And when we divide 28 by 2, we get 14, right? 14 grams. Not to the 7 yet. 14 grams divided by 2 equals 7 grams. 2 half-lives here again. So once again, when you're working these problems out, you're just kind of going the opposite way. And then I do have some extra ones that I'd like for you to try down here at the bottom. They're not extra credit. They're just try and do and see what you come up with. So hopefully this was helpful on finding the half-life of, or the either the amount of a sample left or the age of a sample that is presented.